All right, welcome everybody, and thank you so much to joining us here at Ask Why. My name is Simon Reuning, and today I got the man, the legend, the FAE first responder for the last 22 years, Axel Schmidt here on the call. And Axel, you wanted to talk about fitness. Tell me, how do you define fitness?
Hi, Simon. Thanks for the warm welcome. Yeah, we want to talk about fitness in a traditional way, so not about my physical shape. It's more about the reliability of component. So basically, FIT stands for failure in time, and that's what the topic is about today. So because there are a lot of misunderstanding that I realized when I'm visiting customers, so I want to get it straight a little bit, the terms we are using. So first of all, lifetime. So lifetime is one component, keep a defined property during the defined time. That means it's only the lifetime of one component, which we statistically estimate. Reliability is a number of survivors for a certain population. That means we take dozens or hundreds or thousands, even thousands of parts and test them and see how many of them survived. And that leads to a fit rate, or the Greek letter lambda, and that's basically what stands for abbreviation of failure in time. There's some other terms going around that's probably a little bit misunderstanding. So MTTF is mean time to failure. That basically is what happened with ceramic chips or tantalum chips, because once they're dead, they're dead. There's no way to repair them. In difference to MTBF, which means it's mean time between failures, and that's not applicable for capacitors because we don't repair them. Again, the symbol is the Greek letter of fit is lambda, and the unit for the fit rate is basically 10⁹ pieces hours, or a little bit shorter, it's a billion pieces hours, what we are using here.
Now, before we started our podcast, you were talking about bathtubs and all kinds of curves. Can you explain to me exactly what that bathtub curve actually means and what that concept represents?
Sure. That concept is basically decades old, so it's used also starting in the 50s, and basically describing the how likelihood your application will survive a certain scenario. So on the x-axis for the bath tube, so we have the time, that's the lifetime of the component basically, and on the y-axis we have the failure rate. In the beginning we have a so-called early life failure region. That is typically what the customer don't see, because that's something that we do testing and end of life testing 100%. So we make sure that these parts never show up at the customer side. Then there's a useful life region. That is what you are typically using. And then the interesting thing is when it starts to wear out. That means when the failure rate will be increased. And so what you define as your lifetime of your application.
And so how does fit into this? Like when we start looking at this bathtub curve, I know there's a lot of good examples of when the failures happen, but how exactly does my fit rate actually apply to that curve? Can you explain that a little bit more closely?
Sure. So there are different fit approaches, basically depending on the region, or especially in some cases for companies. So what you see here is what Chemet and YAGEO, or the old Chemet brand and YAGEO, using as basically the MIL standard. So MIL stands for military, HTBK is handbook, and the number is 270F. That's a very established, very old reliability concept. Then we have a Japanese one called JIS standard, what typically the Asian company like Murata, TDK, etc. is using. I'm German, so basically the big company Siemens, they have their own standards brought up in the 70s in the last century, so the SN 29500 as a Siemens standard. And then, of course, we live in a global world. Basically, the ISC standard is what becomes more and more popular, and more people start to using that. And this ISC 61709-1, all this concept based on the same principle. It's a multiplication of certain factors. So there's a base rate. That is basically what Chemet is doing is we collect data over decades, manufacturing data and test data, and then put it into a base rate. And then this base rate will be multiplied with certain factors. A couple of them are really fancy, like the environment. So that's basically something, if you use the military standard, the component, in and ground transportation, or you use it in a rocket or in a missile, that's launched by a submarine, etc., etc. So there's certain factors. You don't have any impact or influence on this kind of parameter. There are two parameters you as a customer have influence. The first one is pi t, that's basically Arrhenius. So that's Arrhenius equation. That means we tested the parts in a certain temperature condition and your application temperature, and then we have something that called activation energy, and from therefore we can calculate the pi t factor. In other words, the closer you come to the upper temperature category, the shorter will be the lifetime of your component. By the way, K, if you use it, is the Boltzmann constant in electron volts. There's another one in joule seconds, so be careful to use the right one. The other and more thing that you can impact is basically the relation between the applied and the rated voltage. And you see here the pi s, that's applied rated divided by a certain factor, that's somehow family dependent, and that's power of 17. So what does it mean if you use less than 50% of rated, so you increase dramatically the reliability of your component? So that's basically the math behind the thing.
So now, when we talked first, the doctors always tell us an apple a day keeps the doctor away. But if we start looking at fit rate, it's not really apples to apples in comparison from different suppliers, is it?
No. So basically, there's a certain difference between that. You see here in the comparison between different suppliers in Chemet and YAGEO. So you have the number of failures that basically we have one failure out of a test time, 2,000 hours, and we have tested 30 components. Under this operating condition, 160 volt, and then as you remember the equation before, so the rated voltage and the operating voltage, and then also the operating temperature and the test temperature. And if we put that all things together, and including a confidence level of 60%, therefore completely different values. So here you see Chemet, when you're testing after the mill standard, you see we have a failure rate of 3.134, while YAGEO has 0.884. And if you compare with other suppliers, basically with Asian ones, using the JIS standard, you see it's a pretty low number. So it's something that's 4 decades lower, as well as supplier B is also pretty low compared to the Chemet YAGEO product, as well as the internal reference. That's more in the range that we're targeting. So basically, the fit rate itself, if you compare different suppliers, it doesn't say something, because in this case here, scenario, we all have the same number of components we tested for the same duration, and we have the same number of failures. So be careful if you compare fit rates without knowing the background, like test condition, number of components, and which standards apply by your vendor.
And right. Well, now that we understand really well how this fit works, how the bathtub works, and how everything is applied, how do we calculate? Do you have an example? Can you give us an example of how to calculate fit rate?
Sure. I mean, everybody should know how you use a fit rate. So here as an assumption, we have a fit rate of 7.22 billion pieces hours, which expressed in a different mathematic way, you see it's 0.0000722. So what are you doing with this very low, small number? So let's imagine you use 1 million pieces in your application, and you want to know how many statistical returns you have after 8,000 hours. And now the math came in. So the failure rate is the number of components that survive minus them that failed. So that's basically this 1 minus e, the exponential power of minus lambda t. Lambda is the fit rate. So we put that into the t and the lambda into the equation. So you see that failure rate at 8,000 hours is 1 minus e power of minus 0 fit rate times 8,000 hours. So that gives you the statistical return rate, the failure rate, which here in this case is 0.0005 something. So if you multiply that with the number of your delivered components, you see that on the last line, you will end up with statistically with 58 pieces in a return. statistically. Again, so the message that we want to bring to you is that that's kind of statistical math. It's not necessarily what really happens in a real scenario. And be careful if you compare different fit rates from different vendors and without knowing the test condition and the standard your vendor applies to that.
All right, well, thank you, Axel. This was extremely informative. Thank you for joining us today, and thanks everybody for watching and listening in. And until next week, just remember to ask why.